Okay, so we have a problem here. So a compound para-aminobenzoic acid, you may have seen it on a bottle of sunscreen, is composed of carbon, hydrogen, nitrogen, and oxygen by the noted percentages. These percentages are by mass. So these are the mass percentages of the compound. Can we find the empirical formula of the compound? So you might want to go ahead and give this a pause, give this an attempt, and see if you can figure this out. And then if you need to, check your work. Okay, so here's how I would solve the problem. I would set this up by trying to relate and really what we want to find is the number of moles of carbon present relative to the number of moles of, say, hydrogen, relative to the number of moles of nitrogen, relative to the number of moles of oxygen. Okay, so if I knew the relative moles in a simple whole number ratio, then I would know my empirical formula. So I want to know what are these numbers here on the formula. So I can start with mass ratios. I know to be true for the sample. 61.31 grams of carbon would be present if we also had 5.14 grams of hydrogen. Also, if we had present 10.21 grams of nitrogen relative to the remainder of oxygen. Just rewriting this, so 10.21. And then oxygen, 23.33 grams of O. And so if I have these grams within this compound, what I would want to do is convert those to moles using the molar masses of each of the elements. 12.01 grams per mole of carbon, 1.008 grams per mole of hydrogen, 14.01 grams per mole of nitrogen, and then 16.00 grams per mole of oxygen. Then stop and work these out here. So 61.31 divided by 12.01. I'm going to go ahead and just pause these and write these in. Okay, so this works out to about 5.1 moles of carbon and hydrogen, 0.7288 moles of nitrogen, and 1.458 moles of oxygen. The next step would be identifying the smallest number that looks like the nitrogen number and dividing all of those by that same number. So I'm going to divide all of these by x, where x is the smallest quantity. This is just mathematically a way that we might get closer to simple whole number ratios. We stop and calculate, and we get our ratio ends up being whole numbers. It'll end up being about 7 moles of carbon present, and it's like 7.01 or something like that. So it's really close to 7.0. So if we go 5.099 divided by 0.7288, that's 7.00 moles of hydrogen. I get a question sometimes, how close should these be to round? The answer should be about within plus or minus 0.05 here. This one's dead on, moles of hydrogen relative to 1 mole of nitrogen relative to 2.00 moles of oxygen. So our formula C7H7NO2 would be our empirical formula for the compound. Okay, so let's say that this compound, which we just determined was C7H7NO2, has a molecular weight of 137.1 AMU from the empirical formula. Now, what is the molecular formula? Well, what we'd want to do is just add up our mass here, 12.01 times 7 plus 7 times 1.008 plus 14.01 plus 16 times 2. That's 137.1. So this compound's empirical and molecular formula are the same. So molecular formula is the same as the empirical formula. But we need to determine this molecular weight, or have some information about that molecular weight, in order to make this determination. All right, so let's look at this practice example. So let's say you have a sample of a compound called phosgene. It's a warfare agent. 2.144 gram sample contains this quantity of carbon, oxygen, and chlorine. what is the empirical formula of the substance. Okay, so we could verify if we want to add these masses together that we get to the sample mass. So we don't quite need this number for the problem of the sample mass. If you want to calculate percent carbon, percent oxygen, percent chlorine, and solve the problem the way we solve the mass percent problems, you could. You don't necessarily have to, because we still just want to realize that we want the ratio of the moles of carbon to the moles of hydrogen to the number of moles of chlorine in this case. Or sorry, not hydrogen here. So the moles of carbon to oxygen to chlorine. Okay, so why don't you give this problem a try, hit pause, and then see if you can solve it, and then check back if you need to. Okay, so we just put in grams of carbon, grams of oxygen, 1.537 grams of chlorine. Use their atomic weights, 12.01 grams per mole of carbon, 16.00 grams per mole of oxygen. This is chlorine, so that's mass of chlorine. So we use 35.45 grams per mole of Cl. Stop and calculate. I'm going to go ahead and hit pause and wrap this up. Okay, so this works out to be 0.0216 moles of carbon to about the same moles of oxygen to a greater quantity of chlorine. So we'll divide these by the smallest, and then that's going to work out to 1 mole of carbon as a ratio to 1 mole of oxygen as a ratio to 2 moles of Cl. So the formula would be CoCl2. And that actually turns out to be the molecular formula as well. The actual structure of phosgene looks something like this. Not that you need to know that, or that you get that from this problem, but if you knew the molecular weight or something about the structure, that's what CoCl2 actually looks like in the case of this compound. Okay, so we talked about this combustion analysis. The key review detail here is that you can have a compound containing CH and O is routinely used. You can also use any random element you wish as this third element, because the way this works is all the carbon mass, you take the carbon mass, is converted to CO2. So you take the carbon mass of CO2 to figure out the mass of carbon in your sample. We then take all the hydrogen in the sample, convert it to water, and then from the water mass, precisely determine it so we can calculate how much hydrogen there is in the sample. And then the third element we just get by simple difference. So we just use difference to get that third element. So mass of carbon from the mass of CO2, the hydrogen mass from the mass of water, just the H mass of water, and then the O mass, or the third element, if we have a random third element, is determined by simple difference. Okay, so when you want to worry about CO2, you want to say, well, you want to use the percent C in CO2, of course, because that tells you how much carbon there is in CO2. You want to use the percent H in water to get the amount of hydrogen in water. Okay, here's a couple examples. Why don't you hit pause, give them a try, check your work, and hopefully see that you arrive at the correct answer. I'm going to hit pause, write the answers in, so in a few seconds the work will appear on the screen. Okay, so in the first part of the problem, I take the mass of carbon in CO2. So I take the CO2 mass times the percent C in CO2. You could write this out a few different ways, but I think this is the simplest way to write it out. We get the mass of carbon. Do the same thing for the mass of hydrogen in water by taking the water mass times the percent H in water. So just 2 times the mass of hydrogen divided by the molar mass of water. That gives us the mass of carbon, the mass of hydrogen. We subtract the grams of carbon and hydrogen from the sample mass. The sample mass is given here in the problem. That gives us the mass of that third element here, in this case it's oxygen. So now at this point, all I need to do, and maybe one point is just recognizing it's kind of a long problem, so we just had to do these first 2 steps in the beginning. Now we can go to the mole ratio. So now we just do the 12.01 grams per mole of C, etc. for hydrogen and oxygen. So I'll go ahead, hit pause, write in the answers, and move on from there. Okay, so we find the smallest quantity of moles, divide all of them by that amount. That's the moles of O. So we get 1 mole of O. Then we get it work out to 3 and 6 for C and H. So we get an empirical formula as C3H6O. So then you do a mass spectrometry experiment or just some sort of experiment to give you the molecular weight. Find out it's 116 grams per mole. What's the molecular formula of the compound? So we just take the 116 grams per mole molecular weight. We're just going to divide it by the empirical mass. So the empirical mass would be 12.01 times 3 plus 6 times 1.008 plus 16. That works out to be 58.08. So we'll say 58 grams per mole. I think you can see that works out to be 2, a factor of 2. So we're going to have 2 units of the empirical formula in the molecular formula. So it would be C3 times 2, H6 times 2, and then O1 times 2. So of course that's C6, H12O2. And so then the way this formula actually looks, it's you don't have to know this for the problem, but it's just the CH3, CH2, 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 1, 2, 3, 4, 5. And then the final carbon, it just goes COOH. So that's 2, 4, 6, 8, 9, 10, 11, 12. So yep, that works out to 12 hydrogen, 6, and then our O2. So it kind of looks like hexanol on the end, but except for it has that carboxylate acid group kind of like acetic acid has. Not a big detail, but just something looking at the actual structure of the molecule. So then we can get quantitative information from reactions, of course. So we see 2 molecules of H react with a molecule of O to produce 2 waters. You can also imagine the mole level. This means 2 moles of a hydrogen react with 1 mole of oxygen to produce 2 moles of water. That the molecule in moles here, the difference is an Avogadro's number is a mole of the substance. So you're going to need 2 times Avogadro's number to have 2 moles of H. And then if you had that, you're going to need just half as many molecules of O, so that would just be 1 mole of O, reacting with the 2 moles of H2 to produce 2 moles of water. Then, of course, you can be given gram quantities as well. Use the molar masses to go back to moles to get these relationships. And then we can recognize that we can mix together any concoction we wish. If we did like 3 H2 molecules, but with 1 O2, we'd have an H2 left over. What we're going to do is usually keep this reaction straight and then try to do some math with it. And the sort of math is, one is, you can make a particle diagram if that helps. Option 2 is make a BCA chart. 3 is just use dimensional analysis to help solve the problem. And 4 is just, think your way through it. If you're thinking your way through it, you're probably using all these 3 other levels to help you there. And even if you're using like dimensional analysis and not necessarily BCA chart, you're probably still thinking of that BCA chart and maybe even the particle diagram. So it's kind of like all these approaches that we mentioned earlier in the video come into play. Hopefully it's part of our understanding of what's going on in these types of problems as we try to find the best possible solution, or maybe just a possible solution that arrives at the right answer. So most problems here will have a few ways we can go about solving the problems, but still hopefully you arrive at the same answer. So the coefficients relate to the number of molecules of the reactants and products present before and after the reaction. And then we can also use mass and molar mass to go from mass to moles. Okay, so we have a problem here relating to stoichiometry. So we can go from, like, say, grams of a reactant, use the molar mass to get the moles of the reactant, use the coefficients from the reaction to calculate moles of some other substance that is either produced or reacts with A, and then use the molar mass of B to go to the grams of B. So imagine maybe we have A to B. You can say, how many grams do you have of A, how many moles? If it's 1 to 1, or if say 2 to 1, you need to use a coefficient. Let's say it's 2A goes to B. We need to use those coefficients to relate the moles of A to B, and then calculate with the molar mass if we want the grams of B. Okay, so a simple problem here. How many grams of CO2 can be produced from the complete combustion of a gram of glucose? Go ahead and hit pause and give this problem a try. I'll write the answer in just a moment. Okay, so I did notice that this said O2, it should say CO2 here, so we're just missing the carbon. Probably noticed that. So glucose plus oxygen goes to 6 CO2 plus 6 waters. So if we have a gram of glucose, we use the molar mass of glucose, so just take 6, 12, 6 O's, add them up. So 180.2 grams per mole of glucose, For every 1 mole of glucose that combusts, we get 6 moles of CO2 that form, and 1 mole of CO2 has a molar mass of 44.01 grams. So we stop, work this out. 1 divided by 180.2 times 6 times 44.01 works out to be 1.47 grams. Okay, here's our final example for this video. Here's a stoichiometry problem. We have barium plus nitrogen forms Ba3N2. We're asked to balance the reaction, identify the reaction type, and then given some stoichiometry problems. So why don't you go ahead and hit pause, and I will go through these problems, hopefully after you give it a shot. Okay, so I've balanced the reaction, takes a 3 in front of barium. The reaction type, we're combining these substances, so this is a combination reaction. And then I've set up a BCA chart, so barium 3 moles, nitrogen 2 moles, don't have any initially of the product present. And so then we're going to lose 3x of the barium for every x we lose of nitrogen. And so then at this point here, we're trying to figure out which or both of these go to 0. So one of the reactants should go to 0. And the question is, which of them is the one that goes to 0? And so you can think of it this way, that if its nitrogen goes to 0, then X would be equal to 2 moles. Okay, and so then barium's going to have to lose 3 moles minus 3 times 2 moles. And that's going to take barium to negative. And so that means I should be left with some of the nitrogen. So nitrogen should be my excess reactant. And so then barium should go down to 0. And if that does, then X is going to be equal to 1 mole. So if we lose 3 moles of barium, X here would be equal to 1.0 moles. And then we're going to lose 1.0 moles of nitrogen, be left with 1.0 moles after the reaction completes. And then we're going to produce 1.0 moles of the Ba3N2. And so if we look, the question says if 3 moles of barium and 2 moles of nitrogen react, which reactant is the excess reactant and how much remains following the reaction? So N2 is the excess, and then 1.0 moles of N2 remains after the reaction completes. Okay, why don't you try the next question and we'll wrap it up in a moment or two. Okay, so the next problem says if 0.75 moles of barium nitride forms, what is the yield of the reaction? We should have formed a mole of barium nitride, and so we only formed 0.75 moles. The percent yield would just be the 0.75 moles that we get, divide by the maximum yield we should have gotten, 1.0 mole times 100%. So this is a 75% yield. Okay, we're going to try the final. The final is actually kind of tricky, but give it a try, and then we'll wrap it up. Okay, so in the last step, we're being asked how much barium should be reacted with excess nitrogen to yield 75 moles of barium nitride. The problem is the yield of the reaction is still 75%, so we really need to figure in here that we're trying to actually produce 75 moles. And we're going to need to shoot for a higher yield in order to get there, given that the actual yield is only 75%, or as a fraction, 0.75. So we need to shoot for a maximum yield here of 100 moles of barium nitride, so that once the yield kicks in, we get the desired 75 moles. And so the problem-solving trick here is just to use the percent yield to help us solve the problem. Then I might use a dimensional analysis step to calculate the moles of barium we need. We need to make 100 moles of with 2 sig figs of barium nitride, and then for every 1 mole of barium nitride that we make, we need to start with 3 moles of barium. So I should mix about 300 moles of barium with excess nitrogen. We should get 100 moles of the barium nitride, but because of the 75% yield, we only get 75% of that, which ends up being the desired 75 moles. So just a way we can use a percent yield to solve a problem like this one here. All right, that's all for this video. Thank you for the attention.